So, last time we started studying the satisfiability problem. So, it was easy to see that SAT is in NP because a satisfiable formula can be easily verified because if you are given an assignment. But the harder thing is that any problem in NP, it can be efficiently reduced to the question of SAT. So, take a problem L in NP and we will show why it can be written as a Boolean formula. So, the idea was that you take the Turing machine that is or the NDTM that is solving L, you think of it as a verifier. Turing machine M is a verifier which is looking for a certificate U, or which is given a certificate U, it will check whether U certifies X via this verifying Turing machine M. So, U is something which you should think of as formal variables, the unknowns. X is the known variable, and in terms of U, we will get a Boolean formula, which in the end we call okay, we haven't reached the end, but so the formula will basically be capturing how one configuration changes to the next via the transition function. Okay, so configuration is a set of variables as many as the cells used on the tapes, input tape, work tape. So, it basically captures this A0 prime to A prime t minus 1 and A0 to A t minus 1, and of course, the state and the head position, right. And we saw that first we break it into the start configuration, compute steps and stop configuration. Start and stop were easy. Compute, we further break it down into steps, right. Assuming time t, there will be t steps. So, here is the description of compute going from C1 to C2, right. C1 was the start configuration, C2 was the stop configuration, and essentially it boils down to checking whether C3 to C4 configuration follows transition I of the transition function delta, and that we can capture. The only point here was that while capturing this, one needs this k prime and k, which are the head positions. So, what are the head positions? How will you find out the head position in the middle of the computation? So, for that we actually assume the Turing machine to be oblivious, so that at the kth step or at the ith step, where the head is, that will be predetermined independent of x. Okay, this can be assumed I as a function, the head position as a function of I, this can be assumed. You do not need to know x or u, u anyways is unknown, but even x is not needed for that, just the length of x will be needed. So, this will be an assignment problem. How do you convert a Turing machine into oblivious Turing machine? And with that, since k is known as a function of I, so this step I can be easily written as a as an AND of equalities, and equalities you convert into AND or not. So, it is a Boolean formula in the end. Okay, so next is point 5, which is, so the formula that we obtained, what did we call it? Did we call it anything? So, in the end we get the formula phi x u, and the property is that phi x u is satisfiable with respect to u, right. So, you can fix u to be 0 1 string if and only if u is a certificate, and hence the Turing machine accepts, and hence phi x u is true, which will happen when if and only if x is a yes, right. Only if x is a yes string, there will be a certificate. So, maybe we write that in the middle. If and only if there exists certificate u, which will happen if and only if x is in L. So, this input string yes will be a yes string if and only if the formula is satisfiable. And what is the size of this formula? It is not a big formula, right. In terms of t, you can see that what we have done is essentially we have these t steps, step I, and within step again there are these at most t comparisons happening. So, it is t square, order t square. Okay, so this now finishes the proof. Thus, we have efficiently reduced L to SAT, and we write it L less than equal to SAT, P referring to the polynomial time reduction that we just gave. Right. So, any problem in NP reduces to SAT, and that is what we promise to prove. Okay. And in fact, we can make this CNF, this formula phi that we constructed, we can make it even more special. The CNF formula phi can be reduced to another formula, can be simplified to psi, which has clauses with only 3 literals. Such that psi is satisfiable if and only if phi is satisfiable. Okay, so in general, a CNF you can always convert into CNF phi, you can always convert to CNF psi, which has only 3 literals in each clause. This is called a 3 CNF. So, what is the proof of this claim? So, a clause which has, let us say, 4 literals, we can break it up into more clauses, each having 3 literal, by introducing a new variable. So, idea is convert clause with greater than 3 literals to more clauses, each having 3 literals. We'll need a new variable for this. So let's just see this in an example, and that will suffice. So let's take phi to be x1, x2 bar, x3, x4 bar. You can convert it to psi, where you look at the first two essentially and the last two. Okay, so you use x1, x2 bar with a new variable z, and then use z complement. Right, so you can see that these two are equal. So just check that phi and psi are indeed the same. Okay, because if both these clauses are true, it's an and, right? So both these clauses are true. So if both are true, if suppose z is 0, then it means that x1, x2 bar part has to be true. And if z is 1, then it implies that x3, x4 bar part has to be true. So we have broken it into two cases. It's basically a case analysis. So in this way, any clause in k literals has an equivalent 3 CNF. Right. So this 3 CNF is, as mentioned before, conjunction of clauses, conjunction of disjunctions where each clause has only 3 literals. And the result that you get now out of this is that 3 sat. What is 3 sat? It's now collection of satisfiable 3 CNF. So phi such that phi is a satisfiable three CNF formula. So 3 sat is as hard as sat. Right. So that is where we are, that if you are given in the input conjunction of disjunctions where disjunctions are only on 3 literals, and the question is whether it's satisfiable or not, then that is as hard as the whole of NP. Okay, 3 sat is NP complete. So here one question that you should do as an exercise, what about 2 sat? And what about special cases of 3 sat? Okay, so 2 sat will have only 2 literals in every clause. And you may also look at settings between 2 sat and 3 sat. So you can come up with such special cases and see whether 3 sat can be further simplified. Okay. So a hint is that 2 sat is actually in polynomial time. Okay, but there might still be interesting things between 2 sat and 3 sat that you can come up with. So let us now formalize this reduction that we just did. So language A is polytime car producible to B, to a language B, if there exists a polytime Turing machine M such that X, the question whether X is in A is a yes string of A or not. This question, Turing machine M will transform X to M of X in B. Okay, so polytime car producible means that that input you can transform efficiently into a different string, which then corresponds to yes string of B, and it's if and only if. Okay, this is a very strong type of reduction, equivalence between A and B, and this is what we define as A reduces in a strong way, so polytime car producible, to B. So B is called NP hard. If every problem in NP reduces to B. Right, this is the term you must have heard before, whether a problem is NP hard or not, or just whether a problem is hard or not. So generally what is meant is that it is so hard, B is so hard that if you solve it, then you solve every problem in NP in this way by using a car reduction. Polytime car reduction is there. Okay, so strings are kind of mapping from A to B. And finally, NP completeness means that B itself is in NP. So B is called NP complete if B is NP hard and it's in NP. Okay, so it's both NP hard and in NP, then you call it NP complete. So the problem is complete for NP. And we can again rephrase what we have just proved as the following theorem. Due to Cook and Levin, that 3 sat is NP complete. right? So this was shown half a century ago, exactly half a century ago, that 3 sat is a problem which is NP complete. And till now what we don't know is whether we can solve it in polynomial time, right? So conjecture is that NP complete means that you cannot solve it in polynomial time, but there is no proof. Though this completeness result we have just shown. So we have shown that for every language in NP, L reduces to polytime car producible to 3 sat. And also 3 sat itself is in NP. Right? There is no doubt because again this 3 sat is just a formula. So when given an assignment you can verify it in trivially. There is a verifier. So 3 sat is both in NP and it is NP hard. So it's bound to be NP complete. So reductions actually are very important in computer science. We use them all the time. They are also important in mathematics, but somehow it is not formalized as such. But in computer science, we formalize it and we use it all the time. Reductions can also be thought of as calling a program subroutine. Right? So you reduce your problem and solve it somewhere else. That basically is the programming idea. Consistent, this reduction is consistent with that programming idea. So some easy properties of reductions. So if A reduces to B, reduces to C, then A reduces to C. Right? This transitivity is it follows from the definition because whatever you will convert x in A to, let's say, m1x in B and then convert that to m2 of m1 of x in C. Take composition and you have path from A to C, a reduction from A to C. So A is NP hard and A is in P. So what does this mean? If an NP hard problem you have found an algorithm, then you have shown every problem in NP is easy. So you have shown that P is equal to NP. And if you have shown P equal to NP, then any problem in P can be thought of as NP hard. Right? So actually these two things are equivalent. It's if and only if. So A is NP hard and A reduces to B. Then what can you do? So NP hard problem, if you are reducing it to B, then B must be harder, right? So B is then at least NP hard. So that is the sense in which we think of NP complete problems as the hardest. So NP complete problems are the hardest in NP. Right, because to whichever problem you will reduce it to, that problem will also become NP hard. if it is a, yeah, so basically this third point is how we can read it like this, that NP-complete problems are the hardest. Every problem reduces to them, and if they reduce to something, then again by proposition 1, your new problem also becomes NP-complete. So 3 SAT, a SAT and 3 SAT are kind of the canonical examples of NP-complete problems. What are the other examples? Are there other examples, natural examples? So other examples are which I mentioned in the overview of the course, first lecture, that traveling salesperson, subset sum or subsum, integer programming. These are all NP-complete. Okay, so these are some practical problems which are known to be NP-complete. How do you show them NP-complete? First, you see that they are in NP. That's easy. Next, you have to reduce from 3 SAT to TSP to subsum to integer programming. Okay, so every reduction you have to work hard. Reductions may not be very easy to come by. So we will not do all these reductions in this course. We will do some simple ones. But you can read off the literature these reductions. It's not important for this course, because there are actually hundreds and thousands of NP-complete problems known. So hundreds of NP-complete. Have been studied, let's say. So NP-complete problems may be infinitely many, but there are hundreds which are actually easy to pose, so-called natural problems. And people have shown reductions. They have given proofs that 3 SAT reduces to all of these. So let us do one simple reduction. So let us show that integer programming is NP-complete. Let's see the proof sketch. So we have already shown that it's in NP. Let's restrict to Boolean solutions. That is, xi is between 0 and 1. So if you restrict to this just 0, 1 solutions by introducing these inequalities, it's clear that it will be in NP. Because if there is a Boolean solution, somebody gives it to you, you can verify it. And now the NP hardness part. This will need more work. So NP hardness part, we will start with a 3 CNF. Let phi be a 3 CNF. So let's convert each clause to an inequality. Okay, let's do that. So for example, if the clause is x1 or x2 bar or x3, then you can write it as, so first of all we want x1, x2, x3 to be between 0, 1. Right, that is the first thing we want, because we want to identify xi's as false and true. Next, we want to make sure that x1 or 1 minus x2 or x3, one of these is, at least one of these is 1. So we just write that down. This is greater than or equal to 1. Okay, that's the system, integer programming system that we have written. Notice that x1, 1 minus x2 and x3, all of them cannot be 0. Right? In other words, x1, x2 bar, x3, all of them cannot be false, because if that happens, then you will get 1 less than or equal to 0. So this inequality actually is implying that the clause is true, and you do this for every clause. Every clause is giving a new inequality. So that's the proof. So this implies that 3-SAT reduces to integer programming, and integer programming with just with Boolean points, Boolean and just 3 variables. 3 variables per inequality. Right, so it's very, very special. You are not even using the full power of integer programming. You are just using integer programs that have that are only looking at 0, 1 solutions, Boolean feasible solution points, and each inequality has at most 3 variables. Already this is NP-complete. So since a special case of integer programming is NP-complete, general case is also. So this conversion which we did from Boolean clauses to arithmetic, this is naturally called arithmetization. From Boolean CNF to algebraic polynomial. This is called arithmetization. You can also call it algebraization. So this arithmetization or algebraization is, we are basically making the original combinatorial question, we are bringing it into arithmetic or algebra. So you saw this linear system, we can also get higher degree systems, which we will get in the next example.